Hi, so today I'm going to be talking about inferring causal effects from observational relational data. This is joint work with Dan Garant and David Jensen. So principally what this work is about is how we can infer the effect of unseen interventions in the case of observational data where we may have network effects. Okay? Just to give a sort of an outline of what that's going to entail. So first I'm going to talk about is the mic not on? Okay. Pause for a sec. Is this better? Okay. So first I'll start with the experimental setting, probably something that more folks are familiar with. And then we'll move into observational causal inference, and then we'll get into the contributions of this work, which is observational relational causal inference, and finally we'll get to some evaluation. So it's probably helpful to start with a motivating example. So consider we're at some social networking site, and we'd like to understand the relationship between privacy settings we give to users and the amount of time they spend on site. So if we're willing to posit that experimentation is something we want to do, then we can take our users and take advantage of randomization, right? So by randomly assigning privacy settings to our users, we can eliminate a lot of the possible biasing effects of confounding. Okay, so what would this look like in this setting? Well, we'd simply define two privacy settings, assume that the default setting is low, and as a treatment, we'll randomly assign some users to high. Okay? We'll measure the amount of time these users spend on site, and then we'll just simply compare the two averages of the treated and the untreated groups, right? And we'll call this our average treatment effect. So you may notice that there's an inherent problem in the formulation I gave you, specifically that in this setting we assume that the treatment status of individuals don't affect other individuals. That is, treating your friends has no effect on you. But if we look at a social network, it's plausible that if we look at a single user, say Chris here, and we look at her friends, the privacy settings of her friends may very well affect the amount of time that she spends on site. So perhaps she sees less content, she's less interested, and as a result, we don't get the right causal effect that we'd like to estimate. So within the experimental setting, Ugander et al. Propose a heuristic to deal with this, namely that first we'll apply a graph clustering algorithm, and we'll get two groups, and then we'll randomize with respect to those groups. So you can see what we're doing here is essentially we're applying an approximation to having you and all of your friends essentially treated, having this counterfactual of the entire network is treated versus untreated. Okay. And in fact, there's been some other experimental approaches that have looked at similar problems, right? So I just talked about this global setting. So this is the counterfactual of the entire network receives treatment versus the entire network stays in control. We can also think about just caring about the effective treating of an individual and explicitly wanting to remove the effect of peer bias. And then finally, we can think about the setting when we want to measure the effect of peers and we're not as concerned with an individual. So there's two issues that we'd like to address. First, each of these require a different experimental design, which can be quite involved, and they also require different estimators. The second thing that is problematic is there are times when we simply do not want to perform experimentation. So the example I just gave you, I think, is a good one, right? Which is that we may not necessarily want to perform an experiment where we're randomly changing users' privacy settings. That might be something that they find distasteful. So the question that we seek to answer in this paper is what can we observe from purely observational relational data? So how well could we approximate the setting where we were able to perform that experiment and estimate these effects? Okay. So it's perhaps helpful to think of work that's already in existence. And in this setting, we'll assume that there's no dependence between people. So again, we'll assume that individuals are independent from each other, that we can treat them in isolation, essentially that we have the IID assumption. So under this, we can use the causal Bayesian network framework, right? This is about 25 years worth of work. Essentially, the idea is that we can use a Bayesian network, which is just a factorization of the joint distribution. It also gives us these d-separation, which is like a set of algorithmic rules that allow us to reason over conditional independencies that may exist in the graph. And under an additional set of assumptions, we can also reason about these causally, right? So an edge between two variables here, say privacy and time on site, indicates that there's a causal effect. That is, if I went and I intervened on privacy, there would be a measurable effect on time on site. And finally, this causal Bayesian network framework also provides a do operator, which is a way to explicitly reason about interventions in the network. So it allows us to differentiate between seeing and doing in a network. This is an important distinction. And the way that works is fairly straightforward. So we start with our network here, and say we want to reason about intervening on privacy and the effect that might have on time on site. You'll see that because this is observational, we have this additional confounder, which is social disposition, so perhaps outgoing people are more likely to have looser privacy settings and also would just spend more time on a social networking site anyway. We can represent what would happen under an intervention by simply removing all incoming edges from privacy, and the resulting graph is the joint distribution after intervention. Okay. So in addition to being able to sort of reason about these theoretically, these interventions, we can also estimate these distributions explicitly from purely observational data using causal adjustment. And causal adjustment essentially consists of two steps. One is identifying an adjustment set using a deseparation-based criterion, and the second is applying an adjustment using a regression model. So perhaps the most commonly used and widely known version of an adjustment set or an adjustment criteria is the backdoor criterion. This was proposed by Pearl some time ago. And the idea is you want to identify a set of variables that you would need to condition on in order to be able to isolate this interventional distribution. Okay, and the criterion is fairly simple. So say we want to reason about the interventional distribution of doing privacy here on the time on site. What we have to do is find a separating set such that no node is a descendant of privacy, so no effects of privacy, and also that set would deseparate privacy from time on site. So in this case, we can just take social disposition, and we can condition on that, and we get that. In the general setting, we can have sort of more complex sets. Okay, but once we have this grouping, what we can do is put it into an adjustment formula. And then essentially what this is just a conditional distribution, and all we're doing is taking a weighted integration over the support of our confounders. And in the case where we're not able to do this analytically, we can think of doing something like a Monte Carlo integration using our data sample and get this estimate. Note that we didn't have to make a parametric assumption to get here. We just need to have some consistent conditional estimate of the conditional distribution, that is. Okay, so we can see how this is, well, hopefully we can see that this is a very powerful tool. The question is, what happens that in this setting we, again, as I said earlier, have assumed that we don't have these relational effects. So how can we extend this framework in order to explicitly deal with these pure effects? So how do we now think about non-independent instances? Well, to deal with this, we're going to use something called relational causal models, which has sort of popped up in the last few years. And this essentially consists of an extension of the Bayesian network framework to an intermediate representation that allows us to explicitly reason over relational variables. I'm going to define that in just 1 second, in a way that we can apply deseparation much in the way that we do in Bayesian networks. So the first step is to define relational variables. The heart of a relational variable is a relational path. So a relational path is simply a way to specify the set of instances that you're going to have, right? So the simplest case is, say we have our user, so U just stands for user here, and say we're starting with just an individual. We can see this is fairly easy to see. This corresponds to sort of the zeroth step of a breadth-first search. We can consider, though, like the first step of a breadth-first search now. So now we can look at the set of users that are friends with a particular user, and we can take the set of their time on site, that multi-set. We can sort of do this recursively. We can think of the value of your friends and friends, et cetera, et cetera. Here we're focusing specifically on this case where we're taking this breadth-first search, but note that any path specification with first-order logic would satisfy this. Okay. Well, using these relational variables, we can then define a graphical model that allows us to do deseparation and then use the criterion as you saw before to estimate effects. This is called an abstract ground graph. So just to show you how these are constructed. So in the case that we have an individual that U0, it's identical to the case I showed you for the non-relational case. However, if we want to extend it to our friends, what we've done is just added the relational variables, and we've drawn in corresponding edges. One thing that's important to note is that a user's friend's privacy affects their time on site, but we've also explicitly said that a user's privacy affects their friend's time on site. So we've encoded semantics of the nature of the relationship into our causal relationships explicitly, namely that it's symmetric. Okay? We can also consider this for friends and friends, et cetera, et cetera. The important thing to note is it's been shown that deseparation applies to this representation exactly as it does in Bayesian networks. So everything we know about how to do regression adjustment and criterion identification applies to this representation. That's exactly what we take advantage of in our work. Okay. So taking advantage of this, we introduced the relational causal adjustment. So essentially, again, 2 steps. The first is just identifying an adjustment set using what we call the relational backdoor criterion. And the second is performing an adjustment using an appropriate set of aggregations and a non-parametric regression. Right. So what does the adjustment set identification look like? Well, it's exactly the backdoor criteria, except applied to the abstract ground graph instead of a simple Bayesian network. So let's say that we'd like to think about the effect of intervening on a user's privacy status and a user's friend's privacy status on that user's time on site. So this was the original example I showed everyone. Using the backdoor criterion, we can see that all we need to do is condition on both a user's social disposition and a user's friend's social disposition. Okay? We also have noticed that we've seen something about the way that information moves throughout the network, because now that we've conditioned on these things, we don't have to consider any sort of second order effects. So we've explicitly said things like friends of friends effects like no longer matter. Okay? So once we've identified this, there's one additional step we have to take before we perform an adjustment, namely that the set of user dispositions isn't a single value, right? It's a set of instances or multi-set of instances. So we need to aggregate it in some way such that we can use it in an algorithm. Now, typically in relational learning, what we would do is choose a set of aggregations, put in some predictive model, and then hope we get good performance. However, we need something a little bit stronger in the causal case because we'd like to be able to say that we've completely conditioned on these values. So if you're willing to say that the effect that your friends have on you is some function from the distribution of their values to your outcome, then we can use the sufficient statistics of those distributions and completely condition on their values, right? So if this is binary data, we can think of something like the proportion of friends that are treated, or if we're willing to make parametric assumptions. In the case where we're not willing or unable to make parametric assumptions, we can also approximate this by taking the first k moments, with the only caveat being that we'd rather overspecify the number of moments rather than underspecify, because we don't want any bias to leak through. Okay? So once we have this aggregation, we can put it into our adjustment formula, which looks very similar to what you saw before, with the only difference is now we also have these relational variables. But this is very nice because now we can use our favorite sort of regression consistent conditional estimator and estimate these effects. Yeah. Okay. And one thing I'd like to point out is before we had all of these different treatment effects that we can think about doing experimentally. Now we can think of these as just operations on the same graph. So essentially we have a unified way to think about possibly very complex interventions that can happen in networks. And this is just sort of a brief overview. We can think of sort of more involved things, and using the same tools that I showed you before, we can estimate them in exactly the same way. So it's a nice way to sort of unify our thinking around these things. Yeah. Great. So now that we have this in place, the question is how well does this work in practice? And specifically, we'd like to know how close to the accuracy that you can get out of an experiment can you get out of the purely observational setting? Now, clearly, wouldn't expect to get the same accuracy because we're doing an additional step of randomization with the experimental setting, but we'd like to know how well we can approximate it. So to do this, we generated a bunch of graphs at random from 2 different models, preferential attachment and the small world network. We varied the scaling factor and the rewiring probability respectively. In the observational case, we had 3 confounders. We varied the strength of the confounding on both treatment and outcome. We also used different functional forms between treatment and outcome, right? So linear and RBF functional forms, so linear and nonlinear. And then we compared our model using gradient boosted trees because we're free to choose whatever we'd like for the conditional estimator against 2 models that explicitly use graph cluster randomization. So in this case, we're comparing against explicitly performing a graph clustering on the graph, randomizing with respect to those clusters, and either using a linear model as proposed by Gui et al. In 2015, or using an inverse probability weighting estimator that was proposed by Ugander et al. The question is, generally, how close can we get? And so the first question we asked was with respect to individual or peer effects. So this is the question of if you only wanted to know the effect on the individual excluding the peer effects, or you only want to know the effect of the peers excluding the individual effect. So we compared only against a linear model in this case because it has a nice decomposition of effects that aren't there for the inverse probability weighting. And then we just compared the marginal effect of individual treatment in the individual case, and in the peer case, we looked at the dose response function of peer effects, looking at the proportion of treated friends from 0 to 1, going by 0.1. And we just measured the mean squared error. Okay? So these are the results. The observational case is in blue, the experimental case is in red. The true effect is 3, so you can see in most cases our bias is relatively close, especially as we get to the nonlinear case, our bias tends to be very close to the linear estimators. Okay. And then finally, we looked at global effect estimation, which is this question, this counterfactual of having treated the entire network or having not treated the entire network. And in this case, we compare against all 3 methods. And again, we measured the error in terms of mean squared error against the actual function that we had access to. And here, just a quick caveat, these are violin plots. So the relative width is the density of the number of times we saw that. What you can, in the top row is a case where we have a small amount of confounding. The bottom is a larger amount of confounding. And what we can see is that when there's a small amount of confounding, we do very well. When there's more confounding, it's a little harder to control for these effects. But again, we get relatively close, certainly within the variance that we see of the inverse probability weighting. Okay. So in conclusion, causal relational models provide a nice framework to explicitly reason about these complex interventions that we can do in networks. That otherwise can sort of be unwieldy both to describe and perform. We can efficiently learn these things from data, which is always nice. And we can have inference of these interventions from observational data that are relatively close to what we can get in the experimental setting. Thanks.
So I wasn't sure that I followed your results slide properly. Which color is your method?
We are blue here.
Okay.
And we are red here. So swap colors on you. But
so does the blue do really well here?
Yeah. So the blue does really well here. But I guess it's important to note that the blue here has access to additional things, which is that there's an explicit experiment happening in that case. So you're actually getting the value of randomization. You're explicitly removing the effect of confounding through that randomization. So we actually wouldn't expect to get smaller bias in the observational case.
Okay, good, thanks.
Questions? Okay, so I do have a quick question. So you talked about having explicit, at least knowing about the possible causal relationship. How explicit do they have to be? So can you deal with implicit causal relationship and infer them, essentially.
Yeah, so there's sort of separate work that we have about learning the structure of these models. That's certainly something that you can do. Yeah, and then once you've learned the structure, you can ask questions about arbitrary interventional effects as well. So I think you can sort of view this within sort of like a larger framework of first learning the structure from observational data and then thinking about the kind of interventions you'd want to perform.
So this is a quick follow-up to the same question, actually. If you go back to your definition of the relational causal model, the graph that you showed, this one. Yeah. So there, the lines, there is a dependence between the disposition of user 1 and the privacy setting of user 0, but no line between disposition of user 1 and disposition of user 0. So is that just an artifact, or is that...
the disposition of user 1 and privacy of user 0, is that the... question?
Yes, so yes, there is a relationship between them. So do you learn this model, or do you need to know this model?
Right. So in this setting, we're assuming that the model's been given a priori, so that we're asserting this model holds true. With the caveat that you are making more explicit some of the assumptions about these rather than just saying they hold. But again, you can learn these models from data if you'd like to.
Okay. Thanks.
Cool.
Any other questions? It's over there.
So a very interesting talk. So my question is whether can you model some sort of like higher level dependencies? Let's say if I play a certain game and I need 3 people to play that game, so 3 of my friends need to be like to play that game so that I can play as well. I need to form a team. Can you model that like just in terms of this model? You need to extend it somehow.
Sure. Is this a question about sort of like causal link formation, or?
Yeah.
So that's a really interesting area. It's not something that's currently has been done, right? So it's certainly an open problem. So dynamic graphs in general are an open problem for causal inference.
We have time for one more quick question.
Hi, you mentioned about the 3 confounding facts when you generate the data. Can you talk more about that, and how do you include in the model? Thank you.
Oh, sure. Like how we generated it? Yeah, sure. So what we did, essentially what we did is we assumed that our all confounding happened from friends. We just randomly generated each of those independently using standard normals, basically. And then we used as an aggregation function the means. And then we just used the logistic function, put those in a logistic function to generate treatment status for everyone, and then just used it in a regular linear model for outcomes. We have code as well that you can, if you're interested in the...
So follow up on that question.
Sure.
These are particular and pretty simple generative models that you use. So how much of effect does it have on the fact that these are actually, they don't encode complicated relationships?
Yeah, absolutely. So I think we've looked at it in some other work when you have sort of these like more higher order dependencies, and in that case, a lot of it comes down to your modeling choices. And this was sort of the point with having enough sufficient moments in order to capture those. If you don't include those in your model, it hurts a lot. But you can get comparable results if you include those, especially if you're doing variable selection in your conditional estimator.
Thank you. Thank the speaker again.